1, 2, 3, 4. Are we streaming now? Maybe. Let's see if we are. We should be. Hello. Yes, we're streaming. Okay. So the deal here is nobody's in the chat right now, but maybe one day someone will be. Hold on. Okay. So at the bottom of the YouTube window, it says basic info, Physics 112, September 19th. That's today's date. And a list of questions. These are the questions we're going to be doing today. There's a lot of them because these questions are pretty straightforward, I think. So if you have any questions or you feel like there's a technical issue that I should address, put it in the chat. And after every question or so, I will check the chat window to see what people have to say. So without further ado, let's start with Chapter 1, Question 5. This is out of your textbook, of course. So turn to Chapter 1, Question 5. That's on page 67, I believe. So let's see. So today's tutorial will help you a little bit about show you some of the applications that we've been doing in class, and it will also help you with your assignment, hopefully. Oh, hold on. There's somebody at the door. Let's see who it is. Hello? Hi. Oh, what's up? Oh, I'm sorry. I'm doing a video thing right now. Oh, so we're streaming live. Do you want to talk to the first years?
No. I don't know.
Okay.
Doing a video?
Yeah. Come introduce yourself. Say hi to the first years. And then I have to get back to work. So speak into the microphone through the pop filter. Yeah. Introduce yourself. Tell them what year you're in.
Hi, my name is Petra. I am a 4th year physics student.
Yeah.
And it's great. You'll do awesome. If I can do it, you can.
Yeah, she was in your guys' shoes, 4 years ago, I guess, huh? Yeah. So now I do a thing where I should do these online office hours. I do regular office hours. But, once a week I solve a bunch of problems so they can see problem-solving techniques.
That's really helpful.
And I stream it to YouTube.
Ooh.
Yeah. All right, get out of here, Petra. It's good to see you. I'm glad you're doing well. Drop by some other time.
I will.
We do need to chat.
Yes. Okay.
Catch up. Where did my pen go? Oh, here it is. Yeah, Petra's great. Okay. So, all right, question 5. Let's start. Okay, so the question says, the position graph of figure P2.5, P2.5 looks like this. There's X, it starts at 6 to 8, and then 10, and then 4. And the graph looks like this. Goes down to 4, and then goes down to 0, t in seconds. So that should be at the bottom of the page right below the question. Oh, you should probably open up your textbooks and read along. Okay. The position on this graph shows a dog slowly sneaking up on a squirrel. Slowly sneaking up on a squirrel. That's this part. Let's see. That's that part. Sneaking up on a squirrel. Then putting on a burst of speed. Must be that. For how many seconds does the dog move at the slower speed? The amount of seconds that it's moving at slower speed is from this time to this time, because that's when it's moving at slower speed. So the answer to question 5A is 6 seconds. B. Draw the dog's velocity versus time graph. Include a numerical scale. And I do this in class too. It's helpful sometimes to, when you're drawing these things out, to draw it directly vertically beneath Let me see if I can get a different color here. So that these line up, it's sometimes pretty helpful. So there's two aspects to this dog's motion. There's this part and there's this part. Okay? So we'll calculate the average velocity in each. So in the first, it goes from 6 to 4. X final is equal to 4. X initial is equal to 6. And it takes 8 seconds to do so. And so I don't know what that is. VAV is going to be delta X over delta T. So it's 4 minus 6 divided by 8. So this is minus 2 over 8. So that's 0.25 meters per second. And why don't I calculate the second one just to be sure? X initial on this one is here at 4 seconds. And X final is 0. And delta T is, how wide's that time interval? 2 seconds. 2 seconds. So, VAV, don't get confused. Let's just clean it up a little. V average is going to be delta X over delta T. It's the slope of that line. So it's going to be 0 minus 4 divided by 2. So that's minus 2 meters per second. Both of these are negative. So let's draw. I guess I'll go back to blue to finish this graph. It's going to be down here. How about if I make this minus 1 meter second, minus 2 meters per second. So for the first little bit, for this time interval, it's moving at average velocity there, so that's probably a quarter. So there is my velocity, and after that time, for 2 seconds, I move that velocity. And there's my answer. Check. All right. Has anybody posted anything in the live chat? No, but 2 people are watching. That probably includes me. So 1 person is watching. Hello. Let's move to the next question. Ooh, that was fun. Next question. So the next question is question 7. A rural male, I'm going to read it out loud. A rural mail carrier is driving slowly, putting mail in mailboxes near the road. Fun. He overshoots one mailbox, stops, shifts into reverse, and backs up until he's in the right spot. The velocity graph of figure P27, okay, and so I looked that one up below, represents its motion. Draw the mail carrier's position versus time graph. Assume that at t is equal to 0, it's in position x is equal to 0. So this is a procedure we talked about in class. The idea is that the area under this graph represents the displacement. Distinguishing between displacement and position is actually a pretty important one. Minus 2. 2, 4, 6, 8, 10. Those are in units of 2 seconds. And so that's time in seconds, and this is in velocity in meters per second. And I'm going to draw out the graph. To tell you the truth, drawing the graph is not a bad idea. 1, 2, 3, so it stays at 3 for there, and then they slow down. Whoa, what did I just do? Maybe I should master this particular application. I've never used this thing before. So, like there's 3, and then for 2 seconds, they go like that, and then for 2 seconds, that was amazing. For 2 seconds, they're like that, and then for 2 more seconds, they're at minus 2 meters per second. Now, this particular issue is one that you're actually going to see a lot of in your calculus class. There's something interesting at play here. All right, so here I've got a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, man, I wonder if I could do this on ruled paper. Graph paper, wouldn't that be great? I don't know. Hold on, I got to do a calculation in my head to set this graph. All of y'all can do it however you want, but I need to do it right because you're all watching me. It's 10 seconds. Meters, no, that's, T in seconds, and then X in meters. Hold on, so that's 6 times 3 is 18, so if I go up in twos, that's fine. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right. So let's start tackling this question. How are you going to do it? The idea here is that I'm going to use the area in this graph to figure out the displacement in this graph. Okay? But like I said before, displacement, it's not position. So to figure out the displacement, I need a starting point, which is kind of a point along this axis. I'm going to start drawing my line. Draw the Mayer carrier's position versus time graph. Assume that x equals 0 and t is equal to 0. So it's telling me that it starts right here. Okay? And I'm going to do this particular question in a bunch of chunks so that you can see. I'm going to chunk up this. Each of these is 2 seconds wide. Okay? So I'm going to calculate the area in each of these. A1, A2, A3, and I'm going to use that information to talk about the displacement in this here graph. So let's start. The area here, A1, it's 2, which is the width, times 3, so its area is 6. So in the first 2 seconds, this time interval, it goes up by 6. So it starts here, and so it goes up by 6. And it ends up here. In the next 2 seconds, again, A2 is 2 by 3, that's 6, and you go up by another 6 to 12. A3 is 2 by 3, that's equal to 6. So in the last one I got to 12, so in the next time, boop, I'm going to go up to 18, which is there. In this one, that time interval, there's no time, there's no area under it. So the next it's a 2 second interval, but then I end up there. And then I'm going to calculate the area in this one, call it A5. A5 is the width of it, like that's 2 seconds. And the height of the graph is minus 2 meters per second. So that's minus 4. So from this time to that time, it goes down by 4 to there. Okay? So the deal is that I'm using this particular graph. Maybe I'll do it in black. I'm using this particular technique to figure out the position of the object at each of these times. And now that I've done that, I can draw a line through them. So it's going to be a straight line through this one, and then a flat line, and then go down. Question B here says, what's the position of the mailbox? The mailbox is where the driver stops. So the position is the mailbox is at 14 meters. That's its location. Okay. Next question is question 29. Let's look. Nobody has anything to say on the live chat. Let's go to question 29. Really? I jumped that far ahead? Okay, well, fine, whatever. I thought I wanted to do question 18 sometime. Oh, wait, I've switched up. I'm sorry. Have I been doing questions and... What? You know what? Oh, but... all of the questions I've been doing are questions from chapter 2. So, retroactively, the questions that I just covered were questions 5, 7 from chapter 2, which are pretty nice. I guess question 7 was already on the list, so I can knock that off. But yeah, I gotta go back. So let's go back to chapter 1. I'm sorry. Chapter 1, page 26. Question 5. I thought those were pretty long for how much time I scheduled. That's funny. Okay, question 5 goes like this. Kiara starts at position x is equal to 23 along a coordinate axis. She undergoes a displacement of minus 45. What's her final position? How do we tackle this question? The idea here is to start tackling a question, we're going to draw a picture. All right. So she says that Kiara starts at position 23. The implication here is that we've already decided on a coordinate system. And then here is Kiara. She is a kitty, I guess. Then she undergoes a displacement of minus 45 meters. Hey, why did you draw the 20? Hey, Dr. Tippett, hey Ben, why did you just decide that positive was increasing? The answer here is that when you're drawing one of these pictures, it doesn't really matter, because the answer will be consistent. I have decided that positive to the right direction is increasing, and that's fine. In this question, the displacement is minus 45 meters. So that's minus this way, 45. So how far over to the right here are you going to go? See, if this far much is 23 of it, then this must here be, let's see, that's 45 minus 23. That distance has to be, do it wrong if I do it in my head, 22 meters. So that's our final position. And so this location is going to be x is equal to minus 22 meters. That's the coordinate location. Hooray! All right, that's question 5. Question 7, still nobody's written anything in the live chat. I guess everything's going fine. Question 7 goes like this. Foraging bees often move in straight lines away from and towards their hives. Suppose a bee starts at its hive and flies 500 meters due east, then flies 400 meters west, then 700 meters east. How far is the bee from the hive? So, like I said, the trick to these is always to start by drawing a picture. So here's the hive. We'll say the hive is at x is equal to 0. So the first step takes you east. I guess east is that way. So the first takes you 500 meters due east. So I'll draw that as a picture. 500 meters. That's there. 500 meters. So we'll say that it's at x is equal to 500. Okay. So the second flight takes it 400 meters due west. West is this way. West is that way. So this displacement can be described as minus 400. And its location there is going to be 500 minus 400, 100 meters. Oh, hold on, someone's knocking at the door. I'll be right back. Hello? Hey, what's up?
You just forgot to sign the
Jeez.
thing. It's not that one, to flip that one over. Yeah, the bottom underneath my name.
Oh, jeez. Oh, I have to sign.
Yeah. Sweet.
There you go.
Thank you.
Thank you. All right, so you might be wondering where this particular equation came from. People like equations after all. What I'm doing is I'm saying x final is equal to the initial position plus the displacement. I know the displacement because I drew it as an arrow. I drew the arrow as this going west, and I said, okay, in that direction it's got to be minus 400, and then I just added that to the initial position to find the final position, 100. And then the last step of it says, there you go, 700 east, which is like that. So that delta x is going to be plus 700 because it's going to the right. So it's going to be x final is equal to 100 plus 700. That's 800 meters. So your final position is at x is equal to 800 meters, and that's 800 meters from a hive. Any questions? One question you can ask is, why do people keep knocking on my door? And that answer is because I'm very popular. Next question is question 29. I'll read it out to you. A butterfly flies from the top of the tree in the center of the garden to rest on top of a red flower at the garden's edge. The tree is 8 meters taller than the flower, and the garden is 12 meters wide. Anusha Shivram just asked a great question, and we will actually, okay. All right, we'll go back to the previous question. So Anusha says, do we have to explicitly state the direction we take as positive when doing the questions? Okay, so one question you might ask appropriately is, where do these signs come from? Why is that minus? Why is that positive? Why is that positive? We were communicated some information. They moved east. They moved west. That's directional information. How did I turn that into positive and negatives? The issue here isn't how you turn it into positive and negatives. The issue here is that you do so in a consistent way. So I decided when I defined my coordinate system that east would be the positive direction. And so in setting up the problem, in drawing the beehive the way where I did, and setting it up so my initial motion in the eastward direction was to a position there, I'm essentially defining for the rest of the problem which direction is positive and which one's negative. I'm doing so implicitly, like I didn't, well, I probably did state outright that I was doing it, but one does not usually state outright that one is doing it. Instead, you draw a diagram, and in drawing the diagram, you show the person reading your solution to the question that you decided to make east positive. So do you need to state it explicitly? It's important when students are at your level to be as clear as you can and as consistent as you can when you're doing one of these problems. And that usually means just draw a picture. draw a picture defining these things, defining east as positive, and then go from there. It's not likely that you'll make a mistake if you do it that way. If you do it just implicitly defining and working it in your own way, it's possible that you'll get the wrong answer and nobody will know why you got the wrong answer. It might be possible that you would say, it might be possible for you to say that the answer was minus 800 meters, which is the wrong answer. But if you included a drawing, say, that suggested that this was at location minus 800, your marker, the person marking your exam, probably me, would see that and say, oh, you know what? That minus sign is there because they're talking about the final position of the bee, but they forgot that we were asking for the distance between the hive and the final position, and not the final location. Okay, so showing us the intermediate steps, or alternatively drawing a really clear picture, means that it will be easier for the people marking your exams and assignments, mostly exams, to interpret what you did and assign you part marks if you got the wrong answer. If you do it right and you get the right answer and you don't show all your work, you'll probably still get most of the marks. If you do it wrong and you don't show any of your work, then you'll usually not get very many marks, part marks at all. The purpose of these things is in part to signal to yourself, but also in part to signal to the people marking or reading your work what choices you made along the way. Okay, so question 29, right on. A butterfly flies from the top of the tree to the garden, and then it goes to a flower. The garden is 12 meters wide, and the tree is 8 meters taller. Determine the magnitude of the butterfly's displacement. Okay, so here's the thing about this question. What people often want to do is they want to just assign numbers to everything, but it's not quite clear in this question where to put the numbers, okay? So to start these questions, sometimes it's helpful to draw a picture. By sometimes it's helpful, I mean you should always draw a picture. Drawing a picture is great. There's a couple reasons to draw a picture, FYI. Oh, wait, that's the wrong color. There's a couple of reasons to draw a picture, and one of the best reasons to draw a picture is that while you're drawing, your brain is actually thinking. And while your brain is thinking, you sort through the issues in these word problems. So what I'm doing right now is a combination. I'm both kind of doodling, not to waste time, but I'm doodling. And in doodling, my brain's kind of sorting out the weirder issues about this problem. And so it's not wasted time to draw a really sweet picture. I said a sweet picture. Yeah, that's nice. Okay. So to reiterate, drawing pictures is sweet. One of the reasons drawing a picture is sweet is that it kind of gives your brain time to think through the problem. But the other reason drawing a picture is sweet is that it helps you parse the information in a word problem. So, there's a butterfly. What do butterflies look like? They look like worms with wings, right? Okay. So it goes from here down to here. And I want to know what its displacement is. I want to know what this vector is right here. So how do I figure that out? It's tricky. Now I've been given some clues. One of the clues says, it doesn't tell me the height of the tree or the height of the flower, but what it does tell me is the difference between the two. So one piece of information that I'm given is how high this interval is. It's not from the tree to the ground, it's from the tree to the level of the flower. And it says that this is 8 meters. And then, it doesn't tell me what the distance from here to here is, But what it does tell me is that there's like a fence here or something. This is the edge. Oh, brutal. Okay, so here's the thing. Let's read this question really carefully. It says that the tree is 8 meters tall and the garden is 12 meters wide. And it says that the tree is in the center of the garden and that the flower is at the edge. But the width of the garden isn't the distance from here to the tree. The width of the garden is from here to the tree to the other fence. It's over here. Okay. So it tells me that this whole region here is 12 meters wide, and that means that this interval from this point to this point is 6 meters. You got to be careful when you do these questions. So that's part of the reason why you draw a picture. You can go back and forth between reading the explanation and drawing. So long story short, my displacement looks like this, where this is 6 meters and this is 8 meters. And it's asking me for the magnitude of the butterfly's displacement. In other words, magnitude. It's asking me how long that length is. And of course, it's a right angle triangle, so its length is going to be square root. We'll use Pythagoras. 8 squared plus 6 all squared. I'm going to take out my calculator and do that. 8 times 8 plus 6 times 6. Take the square root of that. 10 meters. So the butterfly has flown 10 meters. Questions? Question 31. Oops, sorry. Question 31 reads, 3-1. Migrating geese tend to travel in straight line paths at approximately constant speed. A goose flies 32 kilometers south, then turns to fly 20 kilometers west. How far is the goose from the original position? Let me parse this. Oh, let's draw north, south, east, west. North, east, south, west. Okay? And then I'll draw the goose's trajectory. First it goes 32 kilometers south. And then it goes 20 kilometers west. Ooh. The question wants to know what the distance from the initial position is. It wants to know how far that is. This line. It wants to know the length of this line. It's a right angle triangle, so the answer is going to be 32 squared plus 20 squared. 2 times 32 plus 20 times 20. Square root answer. That's 37.7 kilometers. Careful with units. Does anybody have any questions? Okay, so question 34. So I'm going to read the instructions before the questions. It says, simply interpret the problem by drawing a motion diagram showing the object's position and its velocity vectors. Do not solve these problems or do any mathematics. So what it's asking for is a drawing, a position versus, not a position versus time graph, a motion diagram. So that means dots all in a line and velocities. 34 goes like this. In a typical greyhound race, a dog accelerates to the speed of 20 meters per second over a distance of 30 meters. It then maintains the speed. What would a greyhound's time be in a 100 meters dash? Okay. Can I answer this question without using math? Or I'm not sure if the question even wants me to answer the question, but I'll show you how to do it. Just you can get an answer kind of even without math. Typical greyhound race, the dog accelerates 30 meters to a speed of 20 meters per second over a distance of 30 meters. So first it goes slow, small velocity, and then it speeds up, and then it speeds up, and then by the time it reaches here, it's moving at the full 20 meters per second. And then it's going to keep moving at this velocity. So that means the distance it travels, the displacement between each point, is probably going to be the same for each point. And that's how to draw it. Do I know what these times are? No. Also, it tells me not to solve the problem, so I'm going to leave it at that. Question 35. Billy drops a watermelon from the top of a 3-story building. 10 meters above the sidewalk. Billy's so bad. How fast is the watermelon going when it hits? So what's the motion diagram look for that? Well, what did the motion diagram for this one look like? I want you to note on this previous one, there's some issues here. I'm paying attention to two things. The biggest thing I'm paying attention to is the spacing of the points. The spacing of the points indicates how fast things are going, right? So let's try it for this one. Here's what it looks like. Here's Billy and his watermelon. What do watermelons look like? Something like that. And this distance here is, I'll make this x equals 0, and I'll make this x equals minus 100. Okay, why not? All right, so how do I draw this? He drops a watermelon. What happens to a watermelon when you drop it? Well, what happens to anything when you drop it? Does it move as soon as you let go of it from your hands? The answer is no. You let go of it from your hands and it barely moves at all. But then, the longer it falls, the faster it falls. So it gets faster and faster and faster and faster. So as it speeds up, the displacements are going to increase. So first it has a small velocity, and then a bigger velocity, and a bigger velocity, and a bigger velocity, and a bigger velocity, and a bigger velocity. Okay? That's a person dropping something. Question 41. All right, hold on. Anybody have any questions? Anusha, got any questions? Nobody has questions. All right, let's move to the next one. This is question 41. Okay, before then it says problems 41 through 46 show motion diagrams. For each of these problems, write a 1 or 2 sentence story about a real object that has this motion diagram. Your story should talk about people or objects by name and say what they are doing. Okay, so 41, what does the motion diagram look like? First I'll draw the dots. They seem pretty evenly spaced out for the first 4 intervals, but then they get closer together. And then it says stop. What do the velocities on these lines look like? These ones are big. And then the velocities get smaller and smaller and smaller. So what kind of a story can we write? It has to be a story of something that moves at a constant velocity and then slows to a stop. So how about this for a story? Fred the roller skating rabbit. Draw his picture. There you go. And he roller skates, so you got to draw him in a roller skate. Okay, so Fred the roller skating rabbit rolls over nice smooth pavement at a constant velocity, but then he hits the edge of the pavement in the grass. Oh, grass is green. He hits the grass, and the grass slows him down to a stop. Ah, that's a fun story. If only all physics could be reduced to, here's a picture, write a story. All right, question 42. What does 42 look like? I'm going to copy out the diagram as best I can. It says here, and they get closer together right off the bat. And then here it says stop. And then they start getting evenly spaced out again. Wait, I just said evenly spaced out, but I meant they get farther and farther apart. So the velocities look like this. The velocity gets shorter and shorter. But then afterwards, it gets bigger and bigger and bigger and bigger and bigger. All right, cool. So I need to write a story about this. Let's see. What comes to a stop and then goes again? Okay, how about this? I was on my bicycle and I came upon a stop sign. So here I am riding my bicycle. It needs to be a real person. Here's Ben, the guy who teaches Physics 112. Oh, you gotta wear the helmet. Riding his bicycle. He sees a stop sign and he slows to a stop. And then once he's stopped and looked both ways, he starts to speed back up again. Fun. Okay, next question, 44. What does that look like? Turn the page. Whoa, hey, cool. This one says, two parts of the motion diagram are displaced for clarity, but the motion occurs along a single line. Okay. So the motion diagram looks like this. First, they start out pretty close together, and then they get farther apart. And then it says same point. They start to get closer together afterwards. Let's draw the arrows. So first it's a small arrow, and then the arrow gets bigger. And then, oh, the arrow suddenly switches direction. And then it says stop. So what kind of motion does this describe? Incidentally, can you hear me? Is my microphone on? What's going on here? 1, 2, 3, 4. You can hear me all right. Weird. It says it's muted though. 1, 2, 3, 4. 1, 2, 3, 4. 1. Oh geez, is the mute thing even working on this? I don't know. I got asked a question. Can you hear me? All right. Let's ask. Can you hear me? Question mark. Let's ask Anusha. I don't know if people can hear me. Oh, geez. Right here, I'm gonna pause the feed and see if I can be heard. No, wait, I shouldn't do that. Weird. Oh, well, Anusha says they can hear me, so I'll just keep going. Okay, question 44. This stream's kind of weird. What's going on with it? Maybe I'm gonna start and stop it. Yeah, the picture hasn't updated in a while. You know what? Oh, geez. It's not the picture hasn't updated. This thing's not working. Yeah, QuickTime bought the farm. Wait, hold on. I think I know what it is. Hold on. Oh, geez. I've been recording this somewhere. Oh, jeez. Jeez. Stupid image capture. Now I have to find that stupid... It's no wonder. Hold on. Q QuickTime. Jeez. Documents. Oh, get out of here, you. Documents. Size. Where's the stupid... Alright, I'm gonna pause the feed. Hold on.